starting now. So I'll send the go. So just waiting.
Hi everybody, welcome to the final and last week of the MOOC on the power of data science for health and care. You have two of us this week, so we'll introduce each other. So my name is Marilyn Lennon. I'm a reader at the University of Strathclyde. We are the team that developed the MOOC. And my background, if you haven't met me last week or online so far, is I'm very much a digital health researcher. I'm very interested in what we do with data, how we take data from systems, from people, and turn it into more meaningful insight, specifically for health and care practice. And I'll pass over to John.
So hi everyone, I'm John Levine and I'm an artificial intelligence researcher at Strathclyde. And my main interest in this course is in the algorithms and methods that we can apply to data in order to find insights. So what I do is, as I rely on people like Marilyn and people who collect data to actually provide us with an interesting problem, and then I look at the data and I think about what methods can I apply to this? What algorithms can I apply to this in order to find the insights? In other words, how do I choose? I choose a method to try to find insights from the data. I might then pass that back to people like yourselves and say, this is what I've found. And the story doesn't end there. It might be that then you want to collect more data or you want me to apply different methods and things like that.
So that's a great intro actually by accident, John. So last week, Jeanette Hughes and I, so Jeanette from the Digital Health and Care Institute, we chatted a lot about the first steps in AI, right? So we kind of said to everybody, you can't do really snazzy, cool AI until you actually curate and collect and organize good data, right?
Yeah, exactly.
Went through data management and data planning and ethics and governance, and that stuff sounds really boring. But it sounds like you're confirming that, well, actually, you can't do anything cool until you get your hands on some data and start to look at what's actually there. So, well, I guess, yeah, do you agree? Is that like a really important step of the data science process, just getting that data into place? Or
yeah, that's exactly right. All of these modern AI methods, and in fact, Russell and Norvig make this point in their famous textbook, which is now in its 4th edition, that all of these methods are absolutely reliant on good data in the first place, or some data, because all these methods are data driven. We need data and sometimes quite large amounts of data to be able to make any insights at all. The methods that we're using have their basis in kind of mathematics and statistics, trying to find relationships in the data. So yeah, we need the data first. We cannot make any clever insights without the data. So yeah, we're totally reliant on you.
And then the other thing, so some people do have data, right? So I've worked with people where they're like, here's my data, and they want to sort of give me their database or their their Excel files or whatever, and they kind of want to just go, here's my data, put it in a big box and give me back some really good AI. But I'm guessing from my own experience, but I'd be interested in what you think as somebody who develops these models a lot and these algorithms. When you first get a big data set, you also still can't just, press the button and run a k-means analysis, right? So what are those first steps in understanding how to pick the right method? I'm guessing it depends on the data, right? So what do you do first when you get that data set?
Yeah, I mean, it would be a tremendously lucky AI researcher that just received a data set that was completely ready to even run an algorithm on it. But that's not the way it works. Basically, the data that is delivered to you is very raw. It's raw data. Sometimes it's it's a collection of documents or a collection of spreadsheets or all over the place. It's all kinds of stuff. And one of the first things that you need to do is just to kind of explore what data you actually had. Let's keep things fairly simple and say it's just a single spreadsheet, for example, a single Excel spreadsheet. Even given that, you've got to do things like find out what the various columns and rows in the data actually mean, and also what problem are you tackling. This is one of the key questions. So you've got this data. What is it you're trying to do with the data? What would you like to do? So what problem are you trying to address? It may be that you've just got this data and you say, okay, what can I do with this? But often people have got a problem in mind. They might say something like, I run an A&E department and I need to staff this A&E department, and I need to make a prediction of what staff I'll need given the day and given the time. And when I hear the word prediction, that's where my ears prick up and I think that's the problem that we're tackling. So what is it you want to do with this data? Do you want to predict something? Do you want to create what's called a decision support system? That's where you're using the data essentially to allow you to make some sort of a decision about someone or about some sort of case. Basically, it could be a simple true or false decision, could be the amount of something that needs to be applied to something. So in other words, what question are you wanting the data to try to ask? Once you've decided on that, then you've still got a lot to do, because let's say, for example, you were, so in the video, the little video that I did, I talk about regression, where you're trying to predict a value, classification, where you're trying to define a label, and clustering, where you're trying to basically group the data and find out where there are clumps in the data.
You don't know the labels, right, for clustering. You kind of have to figure out whether there are meaningful groups to label later on. And
when you first encounter the data, it may be that you do have a question in mind. So for example, I did a project last summer with one of the MSc in AI students. We have an MSc in artificial intelligence here and applications. And one of the students was working with the NHS, working with a data set, and their project specifically was about trying to predict from someone's symptoms, age, and other factors, how long their stay in hospital would be. And of course, that basically is to try to build up a predictive model of what capacity is needed. So they came into the project with a specific question in mind. And they had some data sets, some huge data sets to try to work this out. So sometimes a data science project starts from that, a question and some large data sets that might support it. But sometimes it just starts from a large data set and saying, is this of any use to anyone? So sometimes it's just a question of starting to explore the data and thinking, would it be useful if I predicted that from all the other fields? Would it be useful if I try to build a regression model of this? Would it be useful? And often, if you're just given a raw data set, one of the first things to do with it is after you've done some initial cleansing on it, is just to try and visualize the data, and then maybe do some clustering on it. So that because clustering, you don't necessarily need a question in your head. So, and that's what we might call kind of exploratory analysis.
And so clustering, would that be categorized as unsupervised then, in the sense that you've not got this pre-defined target outcome thing that you're trying to measure, but you think there might be something, so you're kind of trying to let the model run, or the method run rather, to see if there's something worth building a model on, then you can start to figure out what the labels for those things might be. Is that how that would work?
Yeah, that's exactly right. So there's two sorts of, once you've got your data in a form to do some modeling with, there's two sorts of algorithms. As you say, there's this unsupervised learning, and then there's supervised learning. Unsupervised is the easier method to apply, because all you have to do is for that, you just have to throw what we call a multi-dimensional data set. Now that sounds like a big word, but all that actually means is you've got lots of fields, typically numeric fields, but they might be categorical fields, labeled fields as well. So you've got many fields, and as if you've, it sounds crazy to be talking about a 20-dimensional data set, but all that really means is that you've got 20 columns. And you're trying to see whether, so in unsupervised clustering, what you're doing is just seeing if all the data, basically every row is a point in the data. You're just seeing if those points are close together within that space. So it might be, and if you see clusters within those, it might be that you can give a label to those clusters. It could be that, if you're looking at patients as being, and you've got this stuff, it might be that you've got a cluster up here which are patients who are not at risk from something, and patients down here who are at risk, and it might be that you can actually label these once you've done the clustering. But for doing the clustering, all you need is the data, so you can just throw it at the algorithm. It may be that there's no clusters in the data, but that's quite unusual. And usually, if you do find clusters within the data, then those clusters mean something, and you can give them a label.
And so, is there like an optimum number of clusters, John? Then is there like a kind of perfect number of clusters, or does it just depend?
It just depends. The algorithm will define it for you, basically. You can parameterize and tweak the algorithm to find a given number of clusters, or you can ask the algorithm just to find the kind of optimal number of clusters. So you can run clustering in a variety of ways just to find out what clumps are there. It usually, it tends not to be a kind of one-shot process. You run it, you visualize what you've got, and you look at the numbers and you say, I'll run that again. Typically, when I'm doing clustering, I will be running it at least 4 or 5 times to see what clusters are there. And I might ask it, to try and find 3 clusters, 4 clusters specifically, or that kind of thing.
And so, like, we talked about k-means, sort of clustering methods, didn't we? In one of the classes, one of the activities. So that sort of method that it would do that exact thing. It would cluster, and if you get a new data point, if there are sensible clusters or groupings, if you get a new data point, it would decide which cluster that it's more accurately belongs to. That's that sort of premise,
Yeah, that's exactly right. K-means is just one simple algorithm for doing the clustering. So there are other clustering algorithms, but it's a fairly simple method, and you can even implement it in something like Excel to find the clusters in there. And for K-means, basically you're looking for a specific number of clusters, but you can vary the number of clusters that you're looking for in that one. And then once you've found the clusters, then you can, or if you've already got, so if you found the clusters, or if you've already got what we call labeled data, then you can then move on to what we call supervised machine learning. So in supervised machine learning, basically, if we go back to the Excel version of things, one of the columns is something that you're trying to predict from all of the others. If the column has a number in it, then we're doing regression, and if the column has a label in it, then we're doing classification. Because trying to predict a number is different to predicting a label, we use different algorithms for those two things. So that's when your model starts actually predicting something for you. So going back to the example of the hospital stay, what we had was the model that was developed by the student, which was based on, I think it was either based on neural networks or support vector regression or something like that. Anyway, it was a supervised learning scheme, and it predicted and it tried to predict how long the hospital stay was. So once you've got that, then you can feed into it a brand new point that hasn't got a label, and it will predict it for you. That's the main use of machine learning, in fact.
Yeah. And then so in your students' example, just because it's a nice, clear example, were they predicting the number of days? So like or were they predicting more than 10 days, less than 10 days? Because that would change the method, wouldn't it?
That's exactly right. So they were in fact predicting the exact number of days. So they would. So that's a numerical value. So they were in fact doing regression. So they were learning a multi-valued function effectively that would output that number of days. And I think they were using support vector regression, but they also tried using neural networks in regression mode. Now, if they were doing the other problem, say you just classified it as, like you said, less than 10 days or more than 10 days, that's a classification problem, because you're effectively saying, will this label be true more than 10 days or false less than 10 days? So when you've got a true false thing like that, that's a classification problem, because effectively what you're trying to do is you're taking this data set and you're trying to essentially draw a line through the data to say these are the true ones and these are the false ones. Now, of course, it won't be a straight line. It could be quite a wobbly line. And if you imagine a wobbly line in 20 dimensions, it's probably going to get quite, but basically it's trying to say all the people up here are true and all the people in that area. Or you might have, clustering. It might be that this lot is true, this lot is true, and the rest is false. So you get things like that as well. Yeah,
so the data points, the dots, if it was regression, they can, they don't need to be all tightly fit to a line. They can be.
It can get quite messy. And as I said, with labeling, it might be that this is the space. It might be that there's a cluster of trues up here where the answer is true, and there's also a cluster of trues down here. So it can get messy. But the methods that are used for supervised machine learning can work that out, and can spot that pattern in the data.
And so then where does logistic regression come in? Because we see in basic statistics classes, there's a lot of types of regression. We don't need to know them all inside out for this class. But like you've got linear regression, then logistic regression. What's the kind of basic difference between them? And is that important for the problem of hospital length of stay? I mean, is logistic regression more of a classification method, or is it still in the realms of
so basically, normal regression is where you're predicting a number. Yeah. Logistic regression is where you're using that same technique. So you're predicting a number, but you're using it to predict the value of some, say, a binary variable. Okay. So in other words, you're doing something along the lines of getting a number out using standard regression and then mapping that onto a simple decision variable. So in some ways it's sort of a halfway house between the two. It's using standard regression methods to make something like a binary choice.
Yeah. So in my example then, or your example, which I was using, it'd be like you could have do they stay in hospital for longer than 5 days or not? That would be your binary, and logistic regression would fit for that. Yeah,
so you could apply logistic regression for that, or you could treat that as a labeling problem. So a very typical, and those would both be reasonable methods to use. And typically, as AI scientists, what we do is when we're faced with a difficult data set, we will try a range of techniques on it and see which one works the best. And a priori, we don't know which is going to work. We need to try them on the data. There are subtle kind of variations in the data that will mean that one method works better than another. And we may have a suspicion about what might work well, but then we just have to try. And so in your example, logistic regression would work for that kind of binary decision, or we could treat it as a label. As a typical example of a labeled problem for which logistic regression wouldn't work is where you're given an image of something and you have to say what it is. So you know, when we try this out, typically we use pictures of flowers or animals. So we present the decision system with a picture of an elephant, say, and it has to say elephant or horse, for example. It might be that we've got a database full of elephants and horses that's labeled. It learns from that. Then we give it a new picture. It's never seen it before, and it correctly identifies it. Yeah. One of the big wins or kind of breakthroughs in the last 10 years or so in artificial intelligence is the amount of accuracy we've had at doing that. And I do know that in the health area, the ability to diagnose diseases based on X-rays and those images is now done at least as well by machine as it is by hand. So in other words, the classification of the disease based on an X-ray or based on MRI images or something like that is now extremely good. So yeah,
and I think so. I mean, that was something I was going to ask, but you've just naturally gone into it. So I mean, we love, as analysts, we love structured data, right? That's our best. But in health, well, in lots of fields, but in health and care, there is very messy data. A lot of it's unstructured. A lot of it's quite diverse. So you know, you still get handwritten notes, right, from GPs or pharmacists, and you get images, and of course you can code an image. You can even code, you know, using manual methods or computers. You can start to code text and things, right? So social media companies do that very well. They analyze all our data all the time to see how we're feeling or what we might buy tomorrow. So, you know, I mean, I guess this is a open-ended question, but where do we think that kind of machine learning and data processing is going to help in health and care? Like, what's the future of that? Is that problem solved, or do we still need to work on that?
Well, I mean, that's a huge open-ended question, I think. I think the sky's the limit with these things because AI techniques are being applied. So AI techniques and machine learning, as you say, have been applied to structured data. And while there's still research going on in that area, you know, our colleagues are researching what can be found from structured data all the time. That's a well-researched area. Whereas when you move into the area of, say, text, you know, free-written, handwritten text, you know, in English or other what we might call natural languages, languages that we speak. And when we look at handwritten text or we look at images or things like that, that's less structured data. Then the kind of insights that we can get from that data potentially is very large, but those areas are still being developed. That said, you know, the kind of areas that have been used in analyzing text are getting to be very good. I mean, things like sentiment analysis. Already people take it on board, say, a large number of tweets from Twitter on a particular subject, and then try to work out automatically, you know, what way people are thinking from the kind of vocabulary that they've used and that kind of thing. And neural networks in particular have been trained on those things to try to make predictions from those kind of areas. So certainly textual analysis is something where machine learning is increasingly being used.
It can get quite good. Yeah, I know there's some quite good examples in the mental health area. So there's some quite good examples of looking at Twitter or Facebook posts and trying to detect sentiment, but not just sentiment, not just John feels bad or John feels good, but looking at the context, the keywords around it, and potentially helping at least to predict depression or suicidal tendencies. And that starts to, you know, that showcases how potentially useful the AI or the machine learning could be in a preventative role.
Absolutely.
Diagnosis role.
Yeah. So in other words, data doesn't just mean numbers. It means everything that we might store in a computer. You know, everything can be learned. Stuff can be learned from anything that is stored. And we probably need to think beyond the spreadsheets, as it were, for the next sort of breakthroughs.
I mean, do people still talk about big data, or is that an old term now? So big data it's not just about masses and masses of data quantity wise, but, this future vision that my health and well-being could be monitored in a good way, monitored in terms of, my phone, my Fitbit, and whether or not I've been on TV, whether or not I've used a shower or a kettle. So that data potentially could be very rich, because it's so diverse. It's so many different data streams. So you can fine tune it with dials to kind of really understand how John feels, or if Marilyn needs a GP. So do we still think we're on that trajectory? Although it's ethically quite a scary path, but is that the way we're going in health and care, or even in AI?
Yeah, sure. Okay. Yeah, I think so. I mean, we're now beginning to see I think big data is now a done deal. A few years ago, it was like, oh, we're beginning to collect huge amounts of data. Now it's just accepted that the world is incredibly data rich, and we're now seeing the kind of, like you say, the crossover of big data and what we might call ubiquitous computing. Everything, everything that we do, and as you say, in a good way, is connected to these methods, and may allow us to tap into these methods for enriching people's lives and then enhancing their well-being. I have a relative who is bedbound, unfortunately, and I use sensors and data sources in order to know that he's okay. And in particular, I have a little camera in his room, and I have a system on my phone that alerts me if he moves. So now that's a very simple system. All the camera needs to do is there needs to be a data stream there and some detection, but more could be done than that. So in particular, using AI methods, at the moment I get an alert every time he moves, no matter what. But using AI methods, they could possibly classify his movements into movements that may be kind of a sign of distress, or just simply him moving his covers around and getting comfortable in his bed. So this entire system of so we take it for granted now that the data is fully on and is streaming constantly, and that we can tap into it. What we now need to do is to work out how we can tap into all these systems in order to provide better healthcare, better social care for people, and to be able to kind of respond more effectively and quickly. I think we're now in the area where we're getting all this data, and we now need to make the best use of it that we can in providing the care and healthcare that's needed.
Yeah, I think that's a brilliant point, and probably one of the things that we chatted earlier on, John, when we were chatting, was about AI is about data. Of course it is, but there's always a human element to all things computer science and all things AI. So the data doesn't just work away on its own. So we had chatted about the idea of trust and the human element to AI. So, clinicians need to trust the algorithm, right? Because they don't see it as valuable or trustworthy, they're going to just think that, they'll use their own opinion, right? So things like decision support systems, people need to have faith or trust in the technology. We always have, right? But with AI, I think it's accentuated.
Yeah.
Have you seen any ways that we can, make algorithms transparent, or make what the system's doing transparent, so that people trust the systems a bit more? Do you think that's important?
Yeah, I think it's hugely important to be able to trust AI systems. Let's just say AI systems are now being deployed. AI systems are used in healthcare. They are used in the police force. In they're used in banks and things like that. So we've got to have trust in them. As you know, the way that these things work is that you give them data, and they work out correlations in that data. Now, there have been some instances where AI systems have been given a data set, they've made a correlation between one thing and another thing, and then when people have started So let's say it's a banking support system that says you're given a loan or you're not a loan. And it's made a correlation between, say, someone's credit trustworthiness and something about them. So let's say their age, since I am a slightly aged person. Let's say that these systems have started being ageist, and I say, hey, you didn't give me it didn't give me insurance because I'm over the age of 55. What the heck's going on here? The fact is, it has found that correlation. Now, it may not be that correlation is actually a causation thing. It might not be my age causes my credit untrustworthiness, but it has found that. And so the upshot of this is that we need to test our systems very carefully, but also we have to make sure that there's no accidental bias in the data sets that we give them. The data that we give them is the data that they will learn from. So if there's bias in the data, they'll learn that bias because it is there. So make sure that the data that you give the system is data that you trust and that you think is as bias free as possible. Doesn't mean that you have to doctor it. You have to give it the real data, but make sure that there might be one. If it's heavily biased against old people being a credit risk, and that's not real, there's something wrong with the data. You need to unbias it to make sure it's a full coverage. Yeah, we've talked about that in the course.
Yeah, and I think I've seen examples, in the real world where they've trained their model, say in China, and then trying to use that model in India, and the demographics might be different, the banking loan system might be different, whatever that problem is, there could be something or lots of things that are different. So you can't just assume that the model is going to work for every single scenario, right? Because if I test it on all people called John Levine that have glasses, then it's going to be harder to translate my model, to a wider data set with other people called Marilyn Lennon. So we have to be careful about how quick we are to take a model and just, apply it somewhere else and think it's going to work its magic there.
That's exactly right. So it's always about one is knowing that a model that's been trained on a specific data set is trained for that data set and not necessarily for anything else. Sometimes we can get away with taking a model and giving it and basically applying it to a slightly different problem.
Yeah.
But that's not the problem that the model was trained for. So we do have to be careful. If you want it to apply for a broad data set, you have to give it a broad data set. You have to train it on a lot of data. The other thing is to trust our systems, we have to test them. And it has to be said that in very, very critical situations, we may not trust an AI system unless it's been really, really rigorously tested. So, for example, we've all heard about the Perseverance rover that's on Mars. If I was to put an AI system that had been trained on data and that, well, that getting that thing to Mars costs billions of dollars, and if it goes wrong, we're going to look very silly. So we need it to be tested a great deal in order to trust it. The final thing is actually about transparency, because for some of these models that you've learned, so some of the models like regression models and k-means, it may be clear what's going on. In other words, you may be if it's a simple linear regression model, you can you can see the straight line, for example. But some of these models, like, for example, I've mentioned neural networks a couple of times, it's very difficult to kind of visualize and understand how it's making decisions. Well, there are researchers now, our very own colleague Michael Cashmore works on this, trying to get AI systems to explain their reasoning. So in other words, okay, here's someone, you've described them as not being at risk from cancer. Why did you understand that? So yeah, basically explainable AI, and there is explainable AI will add to the richness. So we've learned very powerful models. If we can then explain why it is that they're dying. Now, it might be that the AI system, for example, can point to one particular input field. Basically, because of that, and because of these data, it seems pretty likely that there's no risk of cancer here, and that kind of thing. So explainable AI is very important.
It is, and sorry, I don't know the viewer's name. I think it was just a username that popped up, but great point, or yeah, great question, because it's very topical, explainable AI, because, you know, AI has been around for a long time, right?
Yeah.
And for lots of reasons, because we've got more data, it took another kind of new lease of life, which is great.
Mm-hmm.
But then, you know, quite quickly we've started to develop these interests, such as, hang on a minute, we need to look at trust, and we need to look at explainable AI, and even on things like, you know, decision support systems, they've been around for a long time as well. But
Yeah.
to convey the information in a usable, understandable, and transparent way, the only way that it's going to go from a really fancy statistics model to something that's a doctor or a nurse or a dietitian is going to be like, this is really cool, I can use this. So that's a good movement in AI to go far further forward in terms of human centered AI, which I know has been around for a while as well, but it's at cusp of coming back into popularity.
And in the history of AI, which is sort of dear to my heart, we started off with things called expert systems, where people tried to actually codify their knowledge into readable rules, but which the computer can understand. But those systems turned out to be not really powerful enough. It was difficult to actually create a set of rules that would make the right decisions. So then we started learning from data, because the data support the decisions. It's just a question of mining that. And we started using things like decision trees. Now, decision trees, you can kind of work out so a decision tree might be to, if you want to find out a particular, you've got a question like, am I at risk of cancer? You'd ask, for example, do you smoke? Yes, no. And it would basically take you down the tree until it worked out what your risk factor was. So you could see the reasoning. But again, the problem with that was that they weren't really powerful enough, these decision trees, to really model the data. So that's when we moved on to statistical learning models and neural networks. Now, the problem with these is that they're incredibly powerful and they can model the data really well. But once they've modeled it, they're essentially a black box. You feed in the data, they go crunch, 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 and out comes the answer. A bit like the famous Douglas Adams, put the thing in, and out comes the answer 42. Well, the problem is we need to know what's going on in the middle. So that's the area of explainable AI. Trying to, it is possible in some cases, to get the AI you can basically trace the query through the neural network with the weights and work out why it's going. But it basically can only be done by hand at the moment. Trying to turn that into a general system where we can inquire of the AI, why did you decide that? That's the next step in our journey.
We're such data geeks, John. No wonder we love this course. I did a project in expert systems in 1988 when I was 12 years old in school. How sad, but it just shows how interested John and I are in data, the power of data. So I think that's probably a good place for us to wind up, seeing as it's certainly in Glasgow in Scotland where we are, it's about almost 5 p.m. on a Friday. So I hope if you tuned in, you enjoyed it. And since this is the last week, please leave comments, good or bad. We always fine tune the course for the next class. If you're interested in further learning opportunities, whether that's just upskilling or whether you want to pursue masters or even PhDs in the future, there's a couple of routes that John and I would love you to look into if you think you qualify. So one is that we run a CPD, so a continuing professional development module. It's very similar to this, but it's kind of this with a little bit more of advanced activities and allow you to actually run some data projects yourself and get your hands on your own data or some practice data. We will make sure you've got the link to that on the MOOC class, so please have a look. And if you're looking further beyond that, we have a huge program of data-driven master's programs, and that's top master's programs at Strathclyde. So we have the AI and applications one that John mentioned. We have a MSc specifically in digital health systems in health and care, which is really popular. And there's quite a few other AI and big data classes that are available from www.strath.ac.uk. So if you look for postgraduate taught opportunities, so that's PGT, you'll find lots of data science and AI driven courses, not just in computing science, but across some of the other faculties such as the business school and the health partners here as well. So thank you very much for joining. Hope you enjoyed it. Please leave us comments. And from John and myself and the MOOC team, thank you very much for taking part in this MOOC.